Hello, today we will talk about derivatives and limits. In several of my previous videos, namely the video on pressure gradient force and stress tensor, and perhaps in few more videos, I referred to certain limits as being derivatives. And if you are not familiar with that mathematical structure, then this might be a mystery for you. Today we will clear up that mystery and I will talk about the relationship between derivatives and limits. In particular, I will geometrically describe limits as well as derivatives and show how they link to each other. I will also prove a derivative using limits, and I will moreover prove three important mathematical theorems that I have been implicitly using whenever dealing with limits, and I will use them even more in future videos. So this is a purely mathematical video today, but I believe it is very important to have it in my series on natural sciences because we are using this mathematics quite often. Without any further ado, let's go and talk about limits and derivatives. To find the relationship between derivatives and limits, I will use function that is kinetic energy. Namely, E is 1 over 2 mv squared, but I will use that mass of air is 1 kilogram, and then I can write, as mathematicians would write, this function E of v is equal 1 over 2 v squared, which means my function E takes v, squares it, and then divides by 2. Now I am asked to find derivative of this. Derivative dE over dV is simply v. By the way, you can see that the derivative of kinetic energy with respect to velocity is simply momentum, because remember, mass is 1 kilogram, so I will have here m. Now, what I need to do is I need to prove that dE over dV is v using limits. Okay, well, that shouldn't be that difficult. dE over dV is a limit as delta v goes to 0 of function E with small increment around v plus delta v minus E at v as delta v goes to 0, divided by delta v. This is further equal to limit as delta v goes to 0. Now I need to substitute this with my actual function. So v plus delta v will be 1 over 2 v plus delta v squared minus E of v, but E of v is 1 over 2 v squared divided by delta v. This is further equal to limit as delta v goes to 0. Now, let's speed up this a little bit. Just when I square this, I will get here v squared 1/2, that will cancel with this. So I will kind of cancel this one and this one. Then I will have cross product v delta v times 2, and that will cancel with this 2. So I will have here just v delta v, and I will have plus 1 over 2 delta v squared divided by delta v. And this is equal, well, I can cancel one of these delta v's, and this will give me limit of, as delta v goes to 0, of v plus 1 over 2 delta v. But this is further equal to limit as delta v goes to 0 of v plus limit as delta v goes to 0 of 1 over 2 delta v, and this is equal to what? Well, this limit is v plus this limit is 0. Limit of delta v, limit of v as delta v goes to 0, it's limit of a constant, and we know that is just constant. And here, limit of delta v as delta v goes to 0, we can forget about 1 over 2 is 0. So I get that this is indeed v, and this is equal dE over dV, which means I proved derivative of dE over dV is indeed v using the limits. The next thing that I would like to do here is to show the relationship between limits and derivatives. And the relationship is the following. We say that the limit of function f of x as x goes to a is equal L if given epsilon larger than 0, we must find delta larger than 0 such that when absolute value of x minus a is smaller than delta but larger than 0 also implies that function f of x minus L is smaller than epsilon. Now let me say this in English. This limit exists given that for a given epsilon larger than 0, we must find delta larger than 0 such that when x is in delta proximity of a but not a, function f of x is in epsilon proximity of L. And this is what the statement means geometrically. This is xy axis, and this is my function. For example, this indeed looks like function 1 over 2 v squared. And now, what is the limit in this case? Well, if I need to find limit as x approaches a, and let's say this is a, and the limit is L, well, then somebody gives me the interval L plus epsilon, L minus epsilon. I go down to my x-axis. I have my interval, this point here, a plus delta, and this point here, a minus delta. I must choose x that is within this interval to make sure that my function f of x is within the interval L plus epsilon, L minus epsilon. Okay, so that's the geometrical and formal meaning of limits. Let's see how this correlates with derivations. Now, if I have the same graph and I have my same function, and you are asked to find derivative at this point, let's call it point P. We know the derivative is tangent, but what does it mean, tangent line? How do we actually find tangent of this point that is fixed? Well, we pick any point, let's say point Q here, and we connect point P with point Q. The connection PQ is also known as secant, namely connection between 2 points on a curve or a circle. Now, because Q is movable, I can move Q towards P and make it as close to P as I want, but never touch P. That's why we have this larger than 0. The difference has to be positive. And then, if I kind of zoom in on this part of the curve, I will get something like this. I will have point P here, point Q here, and now I find the I can connect these 2 points, but because they are so close, this second line is basically tangent line. And then what is the tangent here? The tangent will be function in Q, this is Q, this is P, minus function in P divided by this distance, which is delta x. But what is function at Q? Well, that is f of x plus delta x minus function in P is f of x divided by delta x. And now this is, as you can see, derivative. As long as we let delta x go to 0, delta x go to 0 means Q is approaching P but never touching. It's not equal to 0. And now this is a limit problem, and the limits we explained here in this graph and formally using epsilon delta definition. So I hope from this graph you can see the relationship between limits and derivatives. This doesn't imply they are the same. What I want to say here, this is R, relationship between these two. You remember that in our derivation we had this expression where we said that a limit of the sum is equal sum of the limits, and then limit of a constant as delta v goes to 0 is equal to that constant, and limit of delta v as delta v goes to 0 is equal to 0, and therefore we get v. Now, therefore, the theorem that we need to prove here is that limit of a constant as x goes to a is indeed that constant. Well, to prove this, I will again use my epsilon delta rule. I will say for given epsilon larger than 0, I need to find delta larger than 0 such that when x minus a is smaller than delta but larger than 0 also implies that f of x, but f of x is c, minus limit, but limit is also c, is smaller than epsilon. But notice that c minus c is 0, and since epsilon is larger than 0, 0 is smaller than any positive number. Therefore, I can choose any delta whatsoever, and this will always be satisfied. In other words, in a graphical format, this looks like that. If this is x and this is y, then this is function c, constant. Now I pick any epsilon interval, so this would be c plus epsilon, this would be c minus epsilon, and now I need to estimate limit at x equal a. Well, I can choose any delta whatsoever. This big doesn't matter, because when I go up, I will always collapse to my function c, and I will always be in the interval c plus epsilon, c minus epsilon. The following thing that we also need to prove is the following theorem that says the right one, that says that limit of delta v as delta v goes to 0 is 0. 1 over 2 is just constant, so we don't have to worry about it. So the theorem that needs to be proved is the following. The limit of x as x goes to a is equal to a. To prove this theorem, I will again use my epsilon delta definition. I will say, given epsilon larger than 0, I need to find delta larger than 0 such that the difference x minus a has to be smaller than delta, but also larger than 0, which means x cannot collapse to a. Okay, when I find that delta, this delta also has to satisfy that my function f of x, but that function is x, minus limit, which is a, is smaller than epsilon. And lo and behold, you can see that the left sides, that these are equal, but because I can choose any delta epsilon is given, but delta is my free choice, well, I will just choose delta equal to epsilon, and that will satisfy this condition. Therefore, prove the theorem. Or, in a graphical format, let's say, how is the function f of x equal x looks like? Well, this is how the function f of x equals x looks like. So, if I need to find limit around point A, well, it better be that that limit is A, because function is just f of x equal x, which means if I am given interval A plus epsilon, and here this A minus epsilon, well, because this is 45-degree line, 45 degrees, namely f of x equal x, the same interval will be projected down, so A plus delta, A minus delta is the same as A minus epsilon, A plus epsilon. The last theorem that I need to prove to convince you that everything in our reasoning with limits was correct is to convince you that a limit of the sums is equal to the sum of the limits of two functions. To do that, I will call this limit L1 and I will call this limit over here L2, and the sum of these two functions I will just call h of x. Now I again have to use epsilon delta definition to prove this. So for a given epsilon larger than 0, I need to find delta larger than 0 such that when the absolute value of x minus a is smaller than delta but larger than 0, also implies that the function h of x, which is f of x plus g of x, minus the limit of that function, which is L1 plus L2, is smaller than epsilon. This is, you can go back to this video and see that this is definition of the limits. I'm just using the fact that my function, so-called f of x, is actually f of x plus g of x, and my limit L is actually L1 plus L2. Okay, now I can rearrange this in the following format. I can say that f of x minus L1 plus g of x minus L2, that's the same as the above expression, is for sure smaller or equal than f of x minus L1 plus absolute value of g of x minus L2. In other words, this is well-known fact in mathematics that absolute value of the sum is smaller or equal than the sum of absolute values of two numbers. Okay, now this is where the magic happens. Namely, I cannot change epsilon, that's given to me, but I can always change delta and use any delta to satisfy this expression here. Because I can choose any delta, that means I can choose x sufficiently close to a such that f of x minus L1 is smaller than epsilon over 2. And I can again choose sufficiently clever x such that this difference g of x minus L2 is smaller than epsilon over 2. Okay, now I will substitute epsilon over 2 to be some new epsilon 1. And for this epsilon 1, I need to find delta 1 and delta 2 such that when 0 is smaller than x minus a, and that is smaller than delta 1, also implies that my function f of x minus L1 is smaller than epsilon 1, and for delta 2, x minus a has to be smaller than delta 2 but larger than 0, and at the same time for that delta 2, function g of x minus L2 has to be smaller than epsilon 1. When I find these, delta 1 and delta 2, my delta will be smaller than these two, namely minimum of delta 1 and delta 2. So, picking delta this way ensures that both of these conditions are satisfied. Because if I sum these two, if I sum them up, I will get that f of x minus L1 plus g of x minus L2 has to be smaller than epsilon 1 plus epsilon 1, which is 2 epsilon 1. But 2 epsilon 1 is actually epsilon. But notice that this is greater than this I just showed here. And therefore, if I proved that this is smaller than epsilon, and I just proved it is smaller than epsilon, then this also have to be smaller than epsilon, because this is bigger than this. And that completes my proof that this over here is also smaller than epsilon, and that completes the proof that I can indeed write that limit of the sum is equal sum of the limits. Geometrically, we can easily prove this. Geometrically, we do this. This is x, this is y, and I have two functions. Let's say I have this function, this is f of x, and I have another function, g of x. Now, I need to find limit when x goes to a. So I pick some a, and I go here and I find intersection with my function g of x, and I find intersection with my function f of x. Now, I have to use the same epsilon in both cases. So, I go here, I have limit, this was limit L2, this was limit L1. I take my epsilon interval here, and I take the same epsilon interval over here. Okay? Now you can see that this is delta 2 interval, and here when I go down, this will be my delta 1 interval. What I'm saying, what I said here, pick smaller delta 1 or delta 2, and that one will satisfy both of these conditions, which is true. If I pick smaller one, which in this case is delta 1, because it is contained in this delta 2, I am good to go. I can pick any x that is smaller than this delta 1. So if I pick this to be my x, this point over here, that will satisfy the limit for my function g of x, and at the same time it will also satisfy limit for my function f of x, which means I can simply write that the limit of some of these functions is equal to the sum of the limits of these two functions, which completes my proof, both analytically and geometrically over here. Okay, at this point you might say, listen, I'm really fed up with epsilons and deltas. Was this all so necessary? Why did mathematicians invent these? Well, there are two main reasons. Reason number one, as you saw in this video, and if you are doing a linear algebra, you will see it over and over again. The only way to prove mathematical theorems in this domain is to use epsilons and deltas. So epsilons and deltas are the backbone of analysis, mathematical analysis. The second reason we need epsilons and deltas is the following. Imagine you have this problem. Limit of our function that we started with 1 over 2 v squared as v approaches 10. And this limit is easy to calculate, this is 50. But now someone asks you, how close v needs to be chosen to 10 if we want this function 1 over 2 v squared to be less than some number. In other words, what is the value of v minus 10, what it needs to be. It has to be larger than 0, but what it has to be such that 1 over 2 v squared is smaller than some number, let's say 50.0071. Now you see that you cannot use limits, derivatives, or anything. The only thing you can use to solve this particular problem is epsilon delta definition of limit. Well, that's it. Now you should be more familiar with the concept of limits as well as derivatives, and every time I say this limit is also a derivative, you should thank Newton and Leibniz that worked out these things. If they didn't show up and invent mathematical calculus, then in high school and undergrad studies and graduate studies, you will constantly calculate epsilons and deltas. So make sure you are thankful for these two great men, because you don't have to deal with epsilons and deltas. You can just say derivative of this function is that. Thanks for watching, and I'll see you in the next video.